get started so we can start on time. I do have a lot of content, and we have about an hour. Go a little bit over if we need to, or if you guys want to stay. So this is the agenda today. So this is an introductory meetup. So the reference point is you really don't know much about GPUs and might be getting started in machine learning, and that's fine. You're in the right place. My goal today is kind of more to be broad than super deep, and I want you to kind of walk away with kind of a framework of, okay, what is this GPU? How does it fit into machine learning? How can it get started? Things like that. So this is the agenda. I pretty much will start with like the context, like why do we even care? Why is this important? What can it do for you, basically, right? Talk a little bit about CUDA, which is essentially the framework that's allowing a lot of this GPU acceleration in machine learning. So what that is, kind of a little bit idea of how it works. Then really kind of get into the meat of the GPUs and machine learning. So obviously talk about deep learning a little bit, which is the poster child today, and obviously a big reason why the GPU trend is kind of moving up as it is. But we'll also talk about how you can still apply GPUs to other models, other algorithms as well. And during this, I'll show you as many demos as possible. It's actually training these algorithms with GPUs, so we'll see it running and stuff. And then a little bit about getting started. So if you want to leave tonight and go home and download something, what would that be? What would that look like? Talk about that, and then others. So before we get started, just to help me kind of assess the audience, how many of you are like data science people? So I'm assuming you guys are familiar with the math. How many of you guys are like developer type people, software engineers? Cool. All right. I guess I should say a little bit about myself. So I work at H2O, and GPUs for machine learning is a big deal for us. We've done kind of machine learning in memory distributed for quite a while now, and we're arguably one of the best in the world at that. And we're constantly, trying to, innovate and extend our platform. And so, ML or machine learning on GPUs is kind of a really big push for us nowadays. So I'm a solutions architect. I pretty much am a technical resource. I work with a lot of our customers. So a lot of what I do is not just kind of in the textbooks. I actually, get very hands-on on real-life problems, real-life data, real-life machines, and things like that. So with that, we'll get started. So, like, what is the context? Why do we care about GPUs? Well, the reason is we have a need for more compute, right? This is pretty obvious. We have so much data today. The models that are coming out, like the one I have shown to the left, are getting much more complex, and all that really means is they take a lot longer to train, right? So speed is of the essence. Like, can you wait 2 weeks or a month for one model to get trained? Probably not, right? The good thing is we have the data to train these models, so that's a good thing, right? And usually, a lot of the organizations that I work with, they don't care about just like one model. Like, they're trying to deploy lots and lots of models for many, many use cases. So kind of the iteration cycles to develop machine learning algorithms, put them into production and use cases to drive business impact is a huge driver, right? And that all comes down to how fast can we do it, which drives compute. So historically, the way that we would kind of achieve this is faster clock cycles, right? For those of us kind of that are developers, we know that ultimately how fast your clock goes is kind of a rough order of magnitude, how many instructions you can kind of process with your code, right? And that, I'll show in the next slide, but that's kind of falling out of favor because we just can't keep scaling the clock rates. So kind of within the last decade, we've gone to like multi-core, right? So you can't even buy a CPU today that has a single core, obviously. It's got quad cores, all of that, right? And then obviously distributed computing, right? So if you can't go faster, you can't get any more cores on a chip, then you kind of put more machines, right? That's really the idea. And then so the fourth bullet, which is not there, which is why you're here, is, well, you can exploit GPUs, right, to squeeze a little more compute out of this. So this is kind of the trends that we're seeing. I know it's a lot of lines, but I'll kind of walk through them one by one. So the first top red line is really the number of transistors, right? And that's kind of fundamentally where you've got your scaling from, right? Transistors are the fundamental unit of logic. They're like switches. In fact, my first career was a circuit designer, so I know transistors very well, and you get a lot by scaling them. They've shrunken down dramatically. You get transistors that are 16 nanometers today in gate length. So that's really good. But some other interest, and that's really good for density, right? So they get really, really small. You can put a bunch on a chip, so you get a lot of compute. But you know, a lot of things start flattening out, right? Like the clock rates are flattening out. So at the turn of the century, or a little bit like 2005, like the clock rate, which is in green, is flattening out. So you can't really get much things faster than that. And actually, you're hitting a power wall, right? So you can try to go faster. You can try to put a lot more density, but they're just gonna heat up, and you can't cool them. So right around the time when like power and frequency were kind of plateauing and single thread performance was kind of plateauing, you kind of see the rise of the number of cores. And we're kind of trying to ride that out, right? And then obviously this is just for one CPU. Obviously distributed computing is another big thing, right? Which what we do. So why GPUs, right? Well, you can actually augment your processing that you would do on a CPU with a GPU, right? And why is that? So if you were to try to do 2.3 petaflops, so for those of you who don't know, that's floating point operations, it would be equivalent of like the amount of power you need for 7,000 homes, right? You can use a GPU, which is actually designed to do many, many tasks, and they're much, much more efficient. So if you actually look at specs on, you know, picojoules per flop, it's actually much, much more efficient than a GPU, right? And so the reason why is more transistors on the die are actually dedicated to data processing. Nothing comes for free. I'll explain why they can do this. The items in green are compute logic. I mean that's like part of the die that actually can, you know, do math, add things, right? Everything else is supplement. Their memory, their cache, their control, whatever, right? So this is like a CPU. You got ALUs, which are arithmetic logic units, and here you can see a lot more green. So here's this is probably 2 or 3 years old. I just picked it because I think it's a nice contrast, a nice picture. You can see at the time a Core i7 had 6 cores, 316 gigaflops with 2.3 billion transistors, right? Contrast that to a Titan, which has 2 orders of magnitude more cores, so more compute, can do dramatically much more processing and a lot more transistors packed in to do compute. Right? So that's really the fundamental reason, right? That's how come you can get the compute out of the GPUs. But what you're trading off is latency and throughput, okay? And I'll talk about this. So latency is the time it takes to do a task, right? I take 1 nanosecond to add 1 plus 1, right? Throughput is the number of tasks per unit time. So if I give you 1 minute, how much can you get done in 1 minute? This kind of throughput. So if I kind of do a fictitious example, just to put some numbers on the table, let's assume you have a CPU, and I totally made these numbers up, right? But it takes you 1 nanosecond per task, so that's like a really super smart guy in your company, right? So the throughput would be, let's say you have 6 cores, would be 1 task per nanosecond, 6 cores. You can do 6 tasks per nanosecond. That's really good. That's really small latency, you can do stuff. The GPU is actually 10 times slower. Let's say it's 10 nanoseconds per task, right? So it's 10 times slower, but you've got dramatically much more cores. So per unit time, you actually get a ton of more work done, right? That's really what it comes down to. So the reason why they're able to allocate more of the die for processing is because they're trading off throughput for latency, essentially. So CPUs are latency optimized. They're saying, when I'm given an instruction or sequence, how do I execute that as fast as possible? And GPUs aren't optimized that way. They're optimized more of, given a chunk of time, how do I get as many calculations through my pipeline as possible, right? And that's very fundamental. So this is another picture that I've just shown, more compute. So CPUs are optimized for low latency. A lot of this reason is the way you get the latency is you have things like cache and memory. You can dump stuff real quickly. You do speculative execution, saying, hey, I'm going to guess on what I need to do, and I'll just do it ahead of time, right? GPUs don't care about that. GPUs are like, I'm not going to try to be fast. But I'm going to make it cheap, really cheap, to execute things. So to start threads, super cheap, right? Efficient, power efficient, and I'm going to cram as much of them as possible on a chip. And historically, you would do that because they were really confined to image processing applications, and that just turns out to be what you needed for image processing type applications, GPU. Right? Here's some specs. Latest NVIDIA GPU. I won't kind of go through this. I have it out. You'll have the slides available. So for those of you taking pictures, you can continue taking pictures, but you'll have all these slides. All right, and this is just a projection from NVIDIA, who's arguably the major player in the GPU market, and I'm going to focus on them. They're not the only ones, so I'm not trying to favor NVIDIA over, say, AMD or Intel, but really they have the biggest market share. They have a great ecosystem. So if you get started, you probably want to go with them. What we're looking at here is kind of projections in time, and the y-axis is gigaflops. So how much operations can you do? So you can see in green, which is the GPUs, they're just like an order of magnitude more per second, right? And this really attracted a lot of folks that, in machine learning, like how do we leverage this to kind of do some of our training, which can be parallelizable in some ways. And we'll talk about that, how you can actually parallelize that. So let's pick an example. Let's make it real, right? And so the kind of hello world for GPU programming is a matrix multiplication, right? So let's kind of review, right? So I have two matrices, A and B, and I want to multiply them to get C. So how do you do that? Well, you have two matrices, n by k, k by n, and you're going to make the C. Well, what you do is you take the first row, take the first column, and then you do the dot product, and you get that first element in C, right? And then you repeat for the next one, right? So on and so forth. And then once you're done with one row, you kind of go down to the second one, and you repeat, right? So it's a lot of for loops if you were to do this sequentially, right? You're basically going to say, for each row in matrix A, go to each column in matrix B, and then for each element of the vector, do an element-wise product, sum them all up, and that's how you get to those elements. Okay? So this works. The thing that you should notice here is every calculation in C only requires two vectors. They can be done in parallel. If I gave threads the appropriate vectors, I could compute every element in C in like one shot, versus kind of looping through everything, right? So this is like the hello world. So if you go to like CUDA and you look at kind of their example, you can kind of look at matrix multiplication. So we kind of made a case for GPUs, why they're optimized for these things. Kind of give a toy example that they'll do well in. Now we're going to say, okay, how do you do that? How do you actually? I want to do it now. Like you've convinced me that GPUs are good, they're fast. How do I do that, right? So the way you would do that, arguably, not the only way, but the most popular way, is to use CUDA, right? So historically, GPUs were well suited and used for, well, graphics processing. That's where GPUs come from, right? But people realize that the fine-grained parallelism that is inherent to GPUs can be leveraged for general-purpose computing. But when they first started, what they would have to do would be frame their problems in terms of these primitives that were kind of meant for image processing. So you're kind of like doing a roundabout rigmarole to kind of cast your problem as an image processing problem so that the GPU will do what you want, right? Then in around 2006 and 2007, CUDA came around, and what CUDA did was say, okay, I'm gonna give you an API, a parallel computing platform, and a framework so that you can actually write code normally. You don't have to like contort your problem to image processing problems to leverage the GPU. This is what CUDA stands for. People don't really use it this way today. They just call it CUDA. So this is really the kind of breakthrough 2006, 2007 in terms of making GPUs viable for general purpose computing, right? It took about probably 6 years later till like it kind of made a real big impact in deep learning. We'll talk about that. So how would you use this? How would you use CUDA? Well, so CUDA is a framework and it's a low-level stuff that basically allows you to talk to the GPU. They expose it to different languages. You can do it in C, you can do it Fortran, whatnot. So let's say you have some code that you're going to run, and this is, let's say it's C code, and everything in blue is regular C code, and in green you're like, hey, that's a matrix multiply. Can I delegate that to the GPU and not have the CPU do it, right? And that's the way you kind of write applications for GPUs, right? You do everything that you need to sequentially and make sense to sequentially, leverage the low latency, all that good stuff with your CPU, but then you accelerate your compute that things that can be parallelizable to the GPU. So here's our friend, the matrix multiplication. It's just kind of drawn a different way. Here's A, B, and I'm saying like, hey, really to compute this, I only need a subset of the two matrices. I don't need like the whole matrix. I don't have to, loop through all of them. So how do you do this? So let's kind of do some pseudocode. Well, this is actual code, but we're just going to do the core function and not kind of all the wrapper stuff. So I have a blank string. I'm going to pass this function, matrix A, matrix B, and I want matrix C out, right? And I have a CPU and a GPU, and they both have memory. So historically, the pattern to write CUDA programs is pretty much the same. The first thing you do is you allocate memory. You say, hey, let's see, does this pointer work? You say, hey, you know, I'm going to pass this A matrix, so I know them, so the CPU knows about them. And then you're going to allocate memory on the host. So typically they call the CPU the host. And the way you would do that is instead of using malloc, which is a typical C call for memory allocation, you would use CUDA malloc. So I'd say, okay, let me allocate some space on this memory for matrix A and matrix B, right? And then you do the same thing for B. And then what you do is you then use CUDA memcopy to the GPU memory. Once it's in the GPU memory, the GPU now has access to it, basically, right? And since C is what I want, I don't have to actually like create it in the CPU memory. Now the magic happens. You say, okay, now that I've got in the GPU memory, okay, GPU, go ahead and crunch on all that data that I put in. And the program that you run is what they call a kernel. And so before I talk about the kernel, so what's in this magic function here that I'm passing these functions to? The notation typically you'll see is D is for device, which is on the GPU, right? Because you're using pointers, and then H would be host. So you have a thread. CPUs have threads. They're execution paths that you take. You have to kind of keep in mind. So if you're working at the CUDA level, which I'm just kind of showing you this for background, I don't really expect many of you to code in CUDA. And frankly, you shouldn't have to. There's libraries already that build on this. I'm really just explaining this so you kind of have a sense of like what's actually going on, right? So you have a thread, but if you are programming CUDA, you have to be aware of this level. So when you're programming at that level, you're not abstracted away from the hardware. You actually have to kind of get a sense of the hardware. And that's the reason why I'm going through this. So you have threads. Threads are organized as blocks. There's certain benefits in the block, like block can leverage shared memory, which is a lot faster than global memory. And then blocks, within blocks, they're organized in a grid, right? So when you call a kernel, you have to specify blocks and grids, right? If you don't track everything, it's totally cool. This is really just conceptual. So you have this. They're organized this way. And the way the code works is, all right, let's run serial code. Boom, I'm going to call my kernel, which is basically a GPU program, launch it on all the grids and all these threads, run in parallel, right? Get my answer, and then get it back. And you kind of rinse and repeat, right? So this is essentially the kernel, which is just that last for loop, right? You no longer have to do the iterative thing in the rows and the columns, because that's already taken care of kind of by the blocks and the threads. And all you're really doing is computing the dot product for the vectors that you need, right? So you get your answer back. Once you get your answer back, you copy it from GPU memory back to the CPU, and you free the memory, and life goes on. Continue on. You've got a GPU-accelerated program at this point. Like I said, you typically will not work at the CUDA level unless you really want to. And it's kind of fun. I mean, if you download CUDA, they'll give you samples, and you can compile it, and it works. So you can play with that. But typically, you might not even work at these levels. So a lot of the libraries you'll use, like the deep learning frameworks, they'll leverage these libraries. So you just have to be aware of these in the sense that these are what you might have to install on your machine. You'll install these libraries. So for example, a BLAS, which is a linear algebra kind of library, you'll install cuBLAS, which is CUDA BLAS. So a lot of the low-level matrix-to-matrix operations, matrix-to-vector operations, they already have code here that you can call, and they'll automatically be accelerated by the GPU, right? Magma is kind of like a higher level. You can do like decomposition, matrix stuff, solvers. Sparse is to deal with sparse stuff, random stuff, cuDNN for deep neural networks. That's what the DNN stands for. A math library, and then Thrust. So here's that same code. This was actually a nice demo that NVIDIA did, where guess what they're going to do? A matrix-to-matrix multiplication. And this is in Octave, which is a MATLAB kind of knockoff. And he's going to do C times B. And what he did was he ran it 2 times. He ran it one with the native matrix multiply. And then he went in and replaced every call to the native matrix multiply and replaced it with the CUDA version of it. And recompiled and remade the application. And he did this and said, okay, how many gigaflops do I get as I scale my matrix? And this is kind of a nice chart, right? So if you stay within just the CPU, you kind of like level out, because the CPU is just, it's only going to be able to do what it's going to do with the single threads, right? But then the GPU can really scale. All right, so all of that was just kind of setup stuff. Now let's get to the stuff that you guys are here. So how do I take this and apply it to machine learning? Well, so we're going to talk about the poster child, which is deep learning. How many of you guys know about deep learning, use deep learning? Okay, cool. So a lot of this will be reviewed, which is good. So I can go fast.
Why is it called the poster child?
Because like it's what's it's famous, right? Everyone's like loves deep learning. You put deep in front of your product name or your like company name, and you're going to get evaluated well. GPUs love it, all that, right? If you talk about what's hot in machine learning today, deep learning comes up. That's all. So, right? But that's not the only one. So I'm not going to just play favorites to deep learning. We'll talk about other models and other algorithms in the parallel computing kind of paradigm, right? But deep learning is actually a really good use case. You'll see why when we kind of review like how they actually get trained, right? So deep learning, right? So here's a deep neural network, right? This should be familiar for those of you who are familiar. I'm going to review it for those that aren't as familiar. And if you don't get everything, that's okay. The only part that you'll see that matters is, wow, there's a ton of matrix algebra. If you see that, you're like, okay, great. That's a great place for me to use a GPU-accelerated library, essentially, right? So a deep neural network is consisted of what they call neurons, which are essentially just things that take signal and provide some kind of activation, some nonlinearity, and you cascade a bunch of layers to it. Okay? So the hello world of deep learning is MNIST, which is you have a picture of digits and you want to classify what that digit is. So you can treat a picture as a tensor or a matrix, right? Just think of it as grayscale or RGB, and each pixel is a value. In this case, since it's black and white, I'll just have one layer. One channel, I should say, is probably the better word. And the way this is going to work is I'm going to take a bunch of images, I'm going to show them to my network, right? I'm going to tell the network what the answer is. There's only 10 digits, 0 to 9. Hey, is this first picture a 4 or 5 or 1? And on we go. So what happens inside the network? So what happens inside the network is you'll have a neuron. So one of these little guys that I showed here, right there, right? What does this little guy do? Well, what that little guy does is he says, okay, take all your inputs, apply some weight to them, sum them all up, and then provide a nonlinearity, which we call an activation function. Okay? And that's all I'm expressing with the math here. I'm saying take all the inputs, sum all the weights, add an offset, apply some function G. Right? And this function G is typically one of these guys, which is a nonlinearity that you apply. And then you kind of rinse and repeat. What you get an output from that, and then you'll kind of cascade the layers. Well, guess what? You can kind of see this dot product here. You can think of this as a matrix multiply.
Could you go back to the activation functions? Which one is the latest research?
I mean, people use ReLU a lot today. Classically, they'll use a 10H or sigmoid. Sure. So okay, so for one output H, I'm going to compute this, right? But what if in one shot, instead of just computing one output H, I want all of them, right? So I can express this as a matrix multiplication. So my vector X or my matrix X, each row here is an instance of data. So one picture is one row. And I can have multiple rows, each representing a picture. And then W are the weights associated for each element in the input. The bottom line is you get to something like this, which you don't have to track all the math, but you see a matrix multiply. And that's obviously a big reason why it benefits a lot from GPU acceleration. Okay? Now, that's just a regular multi-layer perceptron neural network. For image cases, you'll probably want to do something like a convolutional network. We can describe why they're different, but you'll see some common operations that you want to do, right? So basically, the multi-layer perceptron neural network doesn't really take advantage of any spatial kind of information you have about the data. It's kind of just like each of the inputs are just looking at whole blob of pixels, right? What you'll see with a convolutional network is you apply some sense of locality. You kind of apply some sense of, hey, pixels that are close to each other matter a little bit more. And this becomes useful maybe when you want to detect edges or shapes or things like that. Okay? So that's really the high-level conceptual idea behind convolutional neural networks. If you think I'm a little hand-wavy, I can answer questions at the end. I just want to get through stuff because I only have an hour. But if you want to come back to anything and dig a little more deeper, I'm more than happy to do that. And I'm really not expecting you to track. For those of you that are new to this stuff, I'm not expecting you to track all the math. I just want you to kind of get the big ideas, really. So this really had tremendous success with computer vision tasks. And if deep learning put GPUs on the map, I would say convolutional neural networks and image recognition put deep learning on the map. And we'll see why. All right, so how does this convolutional neural network work? So let's start with some basic operation. So let's say I have two matrices, X, let's say that's some data, and you have another matrix, which we typically call filter or kernel, an operation that you will do inside a convolutional neural network is an inner product. So all you're doing is doing an element-wise addition, multiplication, and then sum. Okay. So in addition to that, what a convolution will do, so let's say X is your input image, and I have some filter K, so that's just another matrix that I want to somehow apply that inner product to. You'll basically take that filter and you'll slide it across, and you'll apply that same operation. I think you guys obviously already see the independence there, right? And the sliding operation can be parallelized very easily, right? So this is convolution, and I'm applying one filter to one channel. Right? If I just had a black and white image, I would have one channel. If I had a color image, I would typically have red, green, and blue. So I would have 3 of these inputs, and there's no reason why I only need one filter. You can actually, use many filters. And so that's what this kind of diagram is showing. It's a really nice animation that I like from Andre Kaparthi. So what I have on the left is really different channels. You can think of different channels, RGB, and the filter slides across them. And so I'll just show you the cartoon. So this is kind of convolution in action. So what I've got here is I've got a 3-dimensional input, 3-dimensional filter, 2 of them. And I'm just kind of sliding across, and that's how I kind of get my output calculation, right? And you can kind of think, like, conceptually, this output volume is somehow containing information about pixels that are close to each other, right? It's doing that. So this is just another cartoon which repeats kind of graphically what I just said. You'll have your input image, you'll have some filter K, it has some width F. You're gonna perform that inner product, you're gonna apply the activation function, you can slide across all parts of the image, and then you're gonna get some output. We call that an activation map, right? And I can do this not for one filter, but many filters. So what I'm gonna get is for one image, I'm gonna get a bunch of activation maps, which I can treat as another volume. So convolution kind of translates this input volume, this image, which has, width and height and multiple channels of your depth, to another output volume, which has width, height, and input depth. Question? Yep. So they're different, and the network will learn what the filter needs to be. Yeah, sure. So each one of these colors, just think of it, that was produced by a different filter. And what the training of the CNN will do will tell you what they need to be to best suit whatever idea you have, or problem you have, I should say, supervised learning problem or unsupervised. All right, and you can do this as simple for a Linnet network, which I'll show you. This was kind of in 1998, which one of the more popular or famous convolutional neural networks, and then most recently, actually not that recent, probably like August of last year, this is kind of one of the more state-of-the-art ones, which can get very deep, right? Many layers and a ton of matrix stuff, which is prime for CUDA and GPUs, right? So I said kind of let's put it on the map. There's this competition called Well, it's actually called the Large-Scale Image Recognition Challenge or something like that. But they use this data set called ImageNet. You should Google it. Check it out if you don't know about it. And here's some numbers, right? So batch sizes is how many images you're going to feed to the network at one time. You have the GPU training time, the CPU training time, and the GPU, and you can see the speed up. Right? You're getting, 10x speed up. Right? So then you get one question.
You said that same filter we are sliding.
Yes. Yes.
So is it that is the pattern that I am using the ages?
The what?
The age image or something like that. Is that
intuitively, you're not getting the age. The filter kind of learns like image features, right? So like some filters can learn like bright spots. Some filters are more like, hey, can I get the edge outlines? So that's kind of what the filter is learning. They're learning different. The word is features about your input data. Fully connected network. Yes.
Then it is like you have different waves.
Yes.
Here you are using the same wave. But what is the objective of using the same wave?
You don't. Well, you can first of all you can share. You can be sharing. You're not using the same weight, right? So within this kernel, within this filter, and the kernel is kind of the values in there, I guess. You don't necessarily have the same numbers in there. It can learn different numbers in one filter, and you can have multiple filters.
But two of them,
yes.
One filter you are using. What's the objective of that?
The object of that, okay, so the way I think of it, other people might have different interpretations. The way I think of it is, so you see like here I have this filter here, and I kind of start at the upper left-hand corner of this channel of the image. It's going to produce this number 2 for me eventually, right? Well, the objective is maybe that's meaningful in a new image. Maybe that 2 represents a feature about this locality of this image. So the objective is as you're sliding the filter is basically scanning your image and saying, hey, is there a useful feature of this type at that portion of the image? Now, maybe it's going to do that, but it's not going to equally weight them. What I didn't mention is, sorry, that's the annoying part of animation that happen, is essentially you're going to get a fully connected network at the end, right? So it's gonna be able to tune out things that, hey, I like this filter, but I only care about it in the upper left-hand corner. And it really doesn't do much for a certain classification in the middle. So the kernel is just kind of learning what it's learning, but there's going to be subsequent stages that might say, only certain parts of that matter. Sure. Any other questions? All right. So, you won't be programming CUDA, right? You use a library, and actually a lot of the frameworks actually use CUDA, right? So these are popular deep learning frameworks today that basically make use of CUDA and CUDA. And they have a lot of things you would normally do already optimized for the GPU, right? You'll have the convolution ability, you'll have pooling, you have softmax functions, which is awesome. You have to just register to get this one. It's not open source. You don't have access to it. You have the API. So they'll say, hey, you want to do a convolution, like this is what you get it, and this is what we return.
Suppose I'm a Java programmer.
Yeah. Here it is. I don't know how, well, most of it is in C and C++, and you have to get to it.
Frameworks are optimized, but the parallel activations are done by Python.
Yes. Yes.
So there,
I think the part that's not emphasized is the GPU memory and how that is being from CPU to the GPU, how the memory is, how it is do the process, where actually the GPU actually operates.
I kind of explained that earlier.
Oh, you did? Okay.
Yeah, I don't know when you got here. I kind of explained the copying of memory from the CPU. Yeah. So this is a cool graph that I like. So lower years are to the right because the opposite one's to. I'll show you another one that's different. So 2012 was kind of a breakthrough year with a convolutional network that was trained on GPUs with 8 layers, and that's kind of the error rate. And then you kind of see the trend, right? Much more layers, and it's driving down the accuracy. But what's more interesting is if you look at the number of entries from 2012, I only have it to 2014. It's like dramatic growth in people that submit entries now that use GPUs. So in 2012, where you kind of got that breakthrough convolutional neural network that used GPUs, you had 4 entries that were using GPU. 2014, you had 110. I don't know what it is today. I imagine it would be a lot higher than 110. Right? So we at H2O are doing this. So we've had deep learning for a long time. Our approach to this is on a product called Deepwater. And so what we're basically doing is leveraging certain backends, particularly TensorFlow, MXNet, and Caffe. And we're basically providing an API layer to make it easy for you to abstract all the messiness away and basically allow you to kind of make these cool networks for your use cases. So we'll have convolutional networks, recurrent networks, and a hyper.
So what is the maximum cluster size that you use?
I don't have that information. We are targeting that, but I mean, it's still in development. We haven't released it. For now. It's what we're starting with. And I'll show you a demo. So enough talking. I'm going to try to show you as many demos as possible. So is this still up? Yes. No, of course it's not up. All right. Let's see. My process is still running. Yes, it's still running. Yay. More importantly, let's do this. So I'm going to take a look at the GPU. Let's make it viewable. Let me make sure my web browser is responding. Flow. Reload. Okay, cool. All right. So this is loading up. Get rid of this. All right, so I'm gonna turn on, so what I'm looking at here is the driver, and I'm going to keep it on so we can kind of watch the GPU do its thing as I'm training the network. And I'm gonna do a toy example. I'm gonna do that Lynette network. So what you're looking at the screen a number of times is, this is kind of, NVIDIA SMI is just like the driver tool that accesses kind of the GPU. The key thing to know, besides kind of like the usage and how much memory is allocated, you can watch this number here, right, which is the utilization. So at this point, it's 0, not doing anything. And what I'm going to do is I'm going to use our interface to train a neural network, and you're going to see that number go up. So this is H2O Flow. I don't know, how many of you guys have used H2O before? Oh, wow, okay. So only a few of you. For those of you who don't know, it's open source, scalable, distributed in-memory framework that's designed, machine learning framework. And you can access it to many APIs, R, Python. You basically can write code to do what you want. This is a built-in web UI that allows you to kind of do what you need to do if you don't want to program, right? So this is, I'm going to pull up Deepwater. So the way you can access this is you put data, and then you import data. You can read it in from HDFS, S3, whatever you want. But once you've done that, then you can kind of go under the model screen, and this is where you would have access to the different, let me do this, the different algorithms that we have. So we've had deep learning for a long time, and it's best in class, multi-layer perceptron deep learning. And we're going to release Deepwater, which is going to allow you to use the GPU and do kind of like convolutional neural networks, recurrent neural networks, things like that. We might merge them later on just to not confuse people, but that's what it's going to be first. So I've already loaded a a data set just to make things go fast. This data set has images of cat, dog, and mice, and I'm just going to train the network like, hey, is this a cat, dog, and mouse, right? So pretty simple. The key really is just to show you the interface. So I have a label, which is cat, dog, and mouse. I'll do that. I'm going to run it for, I'm going to overfit it just so we can see the GPU going. I'm going to run it for 200 epochs. I'm going to use a Linnet network. And the key is this backend, right? So we're going to support MXNet, Cafe, and TensorFlow. I'm just going to do the MXNet one, which is our most kind of firstly supported one. Then I'm going to build model. So it's going to run the job, and I'm going to go back here, and you can see the GPU going. So it's at 74%. It's trained, it's using the GPU to kind of launch the job, do its thing, and it's going to finish right now. But it's a small data set, 300 observations, and it's not a very big network, just 2 convolutional layers, things like 5 filters in each layer, something like that. So that's deep water. You obviously can do it through Python notebook or R. So this is a notebook that does the same thing. I'm basically loading in the images, so you can see cat, dog, and mouse. And here is the API call, right? So I just say H2O deep water estimator. I want to run this for 500 epochs, and then use this network. I don't have to do that. I can go in and I can say, you know, I want to define my own network. So here I'm defining a graph. And then when I call the API, I basically just say, you know, okay, here's my graph. We'll run that graph, right? And by default, we check for the GPU and we'll use the GPU. And you have to explicitly tell it to turn false if you don't want to. So here's the, this is pretty cool. So in about like 22 seconds, like I said, I'm overfitting, and I know that. But I've gotten observations per second that I'm kind of going through. I ran a case where the GPU is false, just to contrast. So everything's the same, just set GPU to false. You get an order of magnitude less. So in about the same amount of time, 22 seconds, I'm like only 104 observations. So this, you're not going to notice this on a small network and a little bit of data, a big network and lots of data. Question? You don't specify it. You don't have to specify it. That's by default. Deep water will use your GPU. Oh, so they're on your machine. They're a piece of hardware that gets installed. Well, this one that I'm using right now is the cloud, but I have ones in the office. Yeah. So this is running on Amazon, and we have an Amazon machine image that you can try out. So they have 2 GPU instances. They have what is called a G2 instance, or P2, right? I use all of them, depending on what demo I want to do. So this one is running a G2. This one's running at 70 cents an hour. We're a startup.
So since deep water is on top of TensorFlow and so on, we have to install them separately, or they come to the side?
We take care of that for you.
It's all good.
Yeah. That's the one thing we're working on right now, is to make the install. What you'll find if you didn't use deep water, you try to install all of this and try to keep up with all the updates, you're going to have a lot of maintenance to do. So we're trying to add value by taking care of some of that.
Configurability are you involving, like for these frameworks, and how much observability, like, you know, test for this.
Sure.
So how much observability?
Yeah. So the use case here is there's a couple of value propositions. So if you're already an expert at those things and you want ultimate flexibility, you should just work in that framework. We're not trying to replace them. Okay.
It's not something like chaos.
You can think of it like that, but you know, yeah, you can think of that in the sense it's a higher level API and stuff. But really, what we're trying to do is make it easy for folks that are not even deep learning experts. Like, what's the first thing you're going to do when you like try to, you know, train on your network? You're going to be like, give me a network. We have that built in, right? The other thing that we add value, and I'm actually, I'll show you then, is now when you're in the H2O framework, you can leverage other algorithms, right? So you can ensemble a deep water network with a GLM or GPU. The other thing that we do is we provide scoring. So we would generate an artifact that then you could take this model that you trained, TensorFlow model, and then put it in production.
Do you have an ensemble optimizer?
What do you mean by optimizer?
Ensemble, you use different models.
Yeah, so that's stacking, right? So you can ensemble them and add them, but you can provide a learner that learns the best way to like put them together. And we have that. So deep water is a functionality within H2O. So H2O gets released, and with a soon release, we're gonna try to GA deep water. So basically, you download H2O and deep water is there. Deep water is just the name of the project.
I know.
Yeah, we have an AMI you can try. We have a beta release, or I don't call it beta, but a preliminary thing that if you want to just get your hands on it.
Yeah, deep learning. I counted 10 models, different models. Deep learning is really one of them. Is that true? I mean, you put the thing where I counted about 10 different models.
You talking about algorithms?
Yeah.
Yeah.
Models, algorithms, right?
Yeah.
Okay, so there's 10. So the question I have, there's a book on H2O which basically does a lot of demos with the guy who does explain why you use different models for different applications, right?
Sure.
Great. Demos are the way you don't have to use your brain, just demo. But the question is where can I learn how to apply the models to different use cases? Where do I learn that? Because the H2O book doesn't have that.
Yeah, that's true. And that's not the intent of the H2O book. It's to learn H2O. So, I mean, there's a ton of them, and it depends on, like, how, for me, it depends on, like, what your math background is, right? And how deep you want to get, right? So I like, like, elements of statistical learning, right? That's a book that I really like. You can try the introduction to statistical learning, but they still, you kind of require some math, right? And there's other, machine.
So just go back to stats, right? So
it's more than stats, but yes, exactly.
That's a bit.
Yeah. Kind of learning, you want to learn the algorithm, like learn the
Because when I do Python, I've got 50 plus algorithms I can use.
Correct.
But here I have 10. Is that it?
Well, it depends on how you separate the algorithm, right? Like a generalized linear model, like you're going to count that as logistic regression, linear regression. So, question. I'll get to you, I promise. Question.
Along the lines of that, you said that you picked up.
Yes.
If I have to change it, simply add other than
yes. You can't do it from the GUI today. You would have to do it through code.
that's it.
Yes. It's doable. Question with the red hat, sir?
The network topology changed depending on the number of output classes.
Yes. Yes. The output layer changes. Yes. Yeah, I mean that's so that there's an idea called transfer learning where you can train a network, right? And it's gonna be whatever architecture, and it's gonna have some classes on the images that you have, and you can just rip out the output layer, change the number of classes you want, and just train a little bit, and we're gonna probably do it.
Layers, dense layers, that whole thing.
So my current understanding of it is it's still kind of a black art. There's not really a good holistic unifying framework. People try things like, hey, I'm gonna change the stride from 2 to 5, and I'm gonna make the filter from 3 to 7. Let's see if it works. Oh, it does great. Let's submit it, right? But like, I don't want to. It's not 0 or 1. It's not like you have this grand theory and you have like people just guessing. There's stuff in the middle, and it's an ongoing field of research that you read papers for. Just last year they have their first textbook on deep learning that I actually think is great. You can read that.
Yeah, and actually the other way to see it is Google right now has a project where they're using machine learning to optimize on the architecture of the deep learning.
Yeah, exactly.
So,
exactly.
That is to put all our jobs out.
What do you think we do?
So this is great. I really like the questions, guys, and it tells us that we probably need another meetup on just deep water. I do need to move forward just so we get through all the content. And if we get it, we can circle back and ask more questions. Is that okay? Okay, cool. Awesome. But I'm glad you guys are resonating with this stuff, so that's good. I didn't want it to be all kind of slideware and theory, kind of like let's kind of show how you would do this. All right. So we made it through deep learning. Okay, so let's talk about other stuff. All right. So the GPU gives you kind of another level of parallelism, right? You can think of multi-core as a level of parallelism. You can think of distributed computing as that. So how do you break your problem up to leverage parallelism, right? And there's many ways you can break your problem, right? So the first way is model parallelism. So what I'm doing here is I got a model. Can I somehow break it up in a way that I can train it in parallel, right? So the easy one is random forest. So random forest is just a bunch of trees. They can all be grown independently of each other. So you can easily, this is what we call an embarrassingly parallel kind of problem. You just pass all the trees to different nodes and train them independently, and then you can kind of aggregate them there. It gets a little more tricky, but possible, to break up a neural network. So this is a paper from Google, since you mentioned Google, that does just that. You have a really deep, neural network, and you're like, okay, I'm gonna rip off this piece, and I'm gonna train it on one machine, and rip off that piece and train a machine. And obviously now you have the complexity of like, okay, so how do they figure out, interfaces that kind of talk to each other, right? Then you have data parallelism, which is, I'm not going to break up my model, but I'm going to somehow break up my data and use them separately to train the model. So one way is kind of using what they call a parameter server. So the way this works is you replicate the model, and you give each model a different piece of the data to train on. And as that model is training, it's kind of submitting its parameter to a central person called the parameter server. And the parameter server is the thing that's reconciling all these independent training sessions to kind of give everyone the right update to update their portion of the model, or their version of the model. Okay? We do a version of this in our deep learning, right? We launch on different machines that have different data, and each of the machines are training, and they're kind of asynchronously updating the states. Okay, so how would you do it for a kind of more tricky model, like GBM? So when I draw a gradient boosted machine this way, it kind of looks like random forest, right? It's just a bunch of trees, and you're going to add the trees up. The problem is, well, not the problem, but the uniqueness is the way you train a GBM model is not the same way that you train a random forest model. With a GBM model, you have to train them sequentially. So every given tree, let's say tree T, number 3, depends on how you trained tree 1 and 2, right? So in general, some function fi is dependent on all the previous trees and the one that you want to train there. So it is an inherently kind of sequential algorithm, train one tree at a time and do it. And what you're basically doing is you're saying, let's say I have m trees, right? You're saying, okay, for every tree, find the parameter of the tree, which is this what I'm expressing as data, such that it minimizes kind of what I did before. The one way you kind of think of it is it's correcting for errors that it did before, right? That's what it's doing. The point I'm trying to make is I've got this inherently sequential algorithm. How do I leverage parallel computing? Well, this is where you can use data parallelism, right? So if you think about a tree, it's like a classic decision tree, right? You have some node, and the job of the algorithm is to say, what variable should I split on, and what threshold, right? What value of that variable am I going to split on? So let's say the first split is x1, and the threshold is t1. I'm going to, basically get the region in blue. I have the second split, x2, t2, and I'm going to split it up and bottom. And so now you've kind of divided this input space to these little regions, and depending on where your new data falls in, that's how you're going to score it. If it falls in region 1, I'm going to give it this value. If it falls in region 2, I'm going to give it that value. The point I'm trying to make here is that you have to determine at any given point in the tree what variable you're going to split on and what threshold are you going to split on, right? So let's say I start at this top, and I say, okay, what variable am I going to split on? What I should I pick? And once I figure out my I, like what value of I do I split? So how do I cast this problem into something that can leverage parallelism? Well, you do it through data parallelism. So in H2O, we have our data on multiple machines. The data is actually laid out in a certain way. So let's say I have K machines. The data is actually laid out such that each machine gets a chunk of the data. It's columnar. So within a machine, like let's look at the yellow pieces, we call it a chunk. Each chunk is aligned on one machine. So if you want one row in this massive data set, it's on a single machine. You can get that. Okay? So what you can do is you can say, okay, every machine, for the data you have, do math on it. Right? Kind of simplifying it. You can compute the variance or some gradients or Haitian, whatever. Just do your thing, and then combine all that math, do that reduce, to figure out what the optimal x1 and t1 needs to be. But the way I did it was I didn't have to like, I'm scaling through data because I'm doing data parallelism. Right? So this is what H2O does, this is what XGBoost does, and guess what? This operation that you do math, now you're all in one machine. So if you have like a matrix multiply or something, you don't have to do it on CPU, you can do it on GPU. Right? And then you continue. You go to the next layer, but every layer that you're growing the tree, you're doing full data parallelization. So while the algorithm is essentially sequential, you got to build one tree at a time, you can build each tree faster. All right, so let's do that. So let's move some stuff around. We've got our friendly NVIDIA SMI. You can see the GPU here. This. Okay. I got to do some fancy rigmarole because I'm not on our network. Just going to do some setup. Okay. So I'm going to show you the code and what it's going to do, and then we're going to run the code. So this code, basically, I'll show you the piece of the code that's important. The piece of the code that's important is this piece right here. So what we've done in the release that's going to come out is we've kind of integrated with XGBoost, which has basically GPU training capabilities. We're working on our own version, so we have a guy doing just that, taking our GBM for where possible, leverage the things that happen on each node in the GPU, right? And so what this script is going to do is it's going to run a machine leveraging the C in the GPU. No, I didn't want that. Oh, it still worked. Nice. So I'm starting the machine up, parsing things happen because I'm not doing anything yet. And then so I'm building an XGBoost model with the CPU first. So this is doing anything. It's just got a few things because it is a graphics processing unit. So probably like showing my screen or something. So this is gonna run, and right after this, I'm gonna build the GPU version, and then you'll see the NVIDIA SMI file. And so for each, when I'm building the model, you'll see the time it takes to train the model, and then you'll see the error that the model has, and you can compare. So what you'll see, I'll get to the punchline, you're going to see the same error, but you can see it in like 1/10 of the time, essentially. Maybe I should have built, I think I built like 200 trees. I could have built like 100 or 50, just for effect. So this took 50 seconds. And I got an RMSE of like 0.19. Well, first of all, you're not waiting as long because I'm using the GPU. And then this took 10 seconds and got the same RMSE. Oh, did you guys watch this? I wasn't watching this, but this should have fired. But that's how you get speed. So that's it. That's a GBM using GPU. And we're doing this right now through XGBoost, but we're working on our own native version. Cool. So we got a GPU cluster, you can do some math, we have a GPU on it, and I just showed you this, GBM on GPU, right? Where we took our original picture where we can do math on the GPU we offload. All right, so getting to the end of our talk. Actually, we probably went a little bit over since everyone asked questions. Actually, not. Yeah, we're right at time. So I'm going to try to wrap this up real quick because I'm almost done. So the last thing, and this is just kind of my terminology. I don't know if it's official, but the way I think of it is then there's training parallelism, right? So like when you actually have a training process, you're typically not maybe building one model, right? So for example, let's say you're trying to build an ensemble, you're going to build your base layers. Or even if you're building one model, you're going to use cross-validation. Technically, each cross-fold could be a separate model, right? So that's another form of parallelization. Or you can build separate models with separate hyperparameters. So we're going to do that one, okay? And we're going to do a simple model. We're going to do linear regression. So linear regression, for those of you guys remember, you're just minimizing these squares. This is the equation for it, right? It's a line, and you can put it in kind of matrix form, okay? Now, you can extend on this by adding constraints or a penalty to it. So you have ridge regression, which is basically doing the same thing, but it's saying, hey, I'm going to subject this to a budget or a feasible region that is essentially a wall, right? So that's the feasible region. So what you're looking at in this picture is contours of the optimal answer. Let's say the optimal answer, the least square answer is beta hat here, but you can't pick that because let's say it's not in this region. So you have to find the contour that intersects this region, and that's your best answer, right? You can kind of rewrite this in what we call penalty form, and it does the same thing. So you can think of this as now for every beta that you add, you're going to add some penalty. So before the algorithm picks that, it has to be very careful because it says, is the amount of gain I get from it worth the penalty that I'm taking from it? Okay? Again, don't have to worry about the math. Just know that you have regular regression, and you're going to add a penalty. And this penalty can come in many forms. It can come as an L2 norm in the case. If you do a lasso, it comes in an L1 norm, and they have different properties. I'm speeding up because we're kind of about time. The general gist is you're going to have this form. You're going to have the regular least squares term, and then you're going to have a term that mixes your L1 penalty and your L2 penalty. And so I have these parameters, alpha and lambda, that I have to pick. Alpha says, well, how much should I give to L1 penalty, and how much should I give to L2 penalty, right? So for example, if I made alpha 0, the first term goes away, and I only get an L2 penalty. If I made alpha 1, this goes to 0, the first term stays, right? If you're Goldilocks, maybe it's somewhere in between, right? And then you got to pick the right alpha, okay? So I got these hyperparameters that I got to figure out. So I could do it on a single node with a GPU, or I could have multiple GPUs on a single node. So that's what I'm going to put it on GPUs. I'm going to assign GPU, and I'm going to have each GPU sweep the lambda values. So I'm kind of using the GPU to do kind of different versions of my hyperparameters. Huh? Yes. Yes. That's the machine I have actually. So if I go, well, this is my machine right now. If I go add NVIDIA right here, actually, right here. This is my machine, GTX 1080. This one is going to be AWS because I only have one GPU. So now the other woman's question is P2 instance. And I've got 8 GPUs on this P2 instance. And of course, it broke. The pipe is broken. Oh, this one's not broken. Nice. P2s are beefier. They're better GPU cards, and you can get more. Yeah, so this one's about $7 an hour, the one that I'm using now. The largest one you can do is $14 an hour. $14 an hour. So let me go here. Let me do our GLM example. Examples. I'm going to do the C++ Elastic Net version. So all I'm doing here is I'm saying, okay, I want to run a GLM on 8 GPUs. I'm going to run 1,000 lambdas. Take 8 alphas, and I'm going to use 20% for validation. So it's going to take some time, load stuff into memory, start filling it up, and then we can I don't know, this takes like 20 seconds, maybe 30 seconds to load, and then once it loads, you'll see all the GPUs firing at one time. While we're waiting, I can take another question if you guys have questions.
Yeah, you said earlier that you're working a lot with customers. Is there like 3 basic categories that you see in terms of working with customers? They're basically 3 to 5 different use case categories that most people fit in. There's a lot of that, but where is it?
So you're asking, is there a basic category and type of problems that customers are solving?
Yeah.
Or you want to know their the type of customer?
The types of problems.
The type? Well, I mean, at the highest level, it's okay. First of all, now it's going. So you see all the GPUs firing. Watch this for fun. This will take like a couple minutes. Yeah, I mean, if I break it up at the highest level, there's supervised learning and unsupervised learning, right? I mean, that's like 2 big buckets right there. No, and I really can't say. I mean, in the sense that I work, like today I was on a call talking about fraud. I do that. Talk about churn. I do that. There's many, but that's what I like about my job. It keeps it interesting. I get in and I kind of use the knowledge that I've accumulated, my general knowledge, and I apply it to a specific use case. So anyways, that's the idea, and this thing is just going. It's basically solving that equation that I just showed you, that penalized regression that I showed you, on 8 GPUs, each one getting a different alpha, and then I'm doing a search on the macros. Right? So 3 algorithms, 3 use cases, and then I'm gonna wrap up. I'll hang out, obviously. So if you want to get started, like how do you do this, right? Go download CUDA. You don't have to do anything, just download it. Pick your thing, pick your operating system, architecture, stuff like that. To download CUDA, you do need to register. They're gonna force you to like give your email. So either you do it or you get a friend and you guys share the file, whatever. You can go to our website, and there's a link to the AMI. Again, I'm going to just put an asterisk is that we're not officially release it. You're going to run into bugs, things like that. But if you want to just play with it, you can go do that. I helped build this, so it's okay. We're working to make it a little bit more stable and add more features. But you can do that today after you go home if you want to play with it. So the AMI will be on AWS, and that will be a Linux box. You should select that. Other things that we didn't get to talk about that are kind of important. So I talked about multiple nodes and a single GPU. You could have multiple nodes with multiple GPUs each. So like you got a lot of money now, and you got a lot of parallelism options, right? But you have to it's a game, right? You gotta when you're developing this stuff, you wanna, especially if you care about speed, you gotta kind of make the CPU, the GPU handoff, and all those things efficient. Keep them busy. Right? You don't want to make one thing idling waiting for the other. That's fine. You got to think about communication, right? The overhead, things like that. NVIDIA is working on kind of this thing called NVLink, which is going to make the communication between GPUs a lot faster. You can check that out. And you don't have to use GPUs for training. There are actually optimizers that help take a trained network and then optimize for inference or scoring, right? Both in terms of the software and as well as the hardware. And if you're attending GTC, you should come hear our CEO talk about machine learning and AI on GPUs. He'll do a keynote. And if you're actually here and you actually want to learn about deep water, myself and some of my colleagues will be teaching a class on deep learning using H2O deep water. So we'll kind of be hands-on. You can actually type on the keyboard, build a model, compare them, all these things. This, I think our date was May 11th. Yeah, May 11th. But the conference is May 8 to 12. So it's here. It's here. All right. That's it. Questions? Thank you. Gentlemen. Yeah. Well, so the one obvious thing is, for example, so your GPU is gonna have some memory, right? So one option you have when you like train a deep learning network is what the mini batch size is. Like how many images do you give the network to train at a given time? You probably want to optimize that number so that you maximize all the memory you have, right? So if you have so much memory in GPU, but you're only giving 10% of that memory for images, like you could crank that up a little bit more. So little things like that. But you're right in the sense that a well-designed framework should take care of that for you as a machine learning practitioner. I agree with you.
So that is another question. So you can buy the GPU with 8 bit memory.
That's right.
6 bit memory.
Yes, sir.
So do you do optimization under it?
We don't. We just let you pick and we're going to dump it, and if you don't have memory, we'll do like you don't have memory. But that's something we could do. I mean, we would have to query the GPU and say that. But that's typically a hyperparameter you pick, because it doesn't only affect the memory, but the batch size you give to the network affects your training. Right? That's how often you update your grades. So, yes. Yep. Yeah. Okay. So the use case or H2O? Just the use case? Yeah. Okay. So fraud is an interesting use case. So fraud has some unique characteristics in the sense that it's rare, hopefully, right? So how do you kind of train a classifier if you want to detect fraud, no fraud on that? So that's kind of where you have to be aware of like how you weight certain samples, what your metric is when you measure fraud. So like, huh? Oh, you could do images. You could do images. Exactly, but you can cast the problem to images. You're right. You're right. Exactly.
What's better, two for GPU or one?
One with 8. One, given that the GPUs are the same.
Given that the machine can support.
Well, and they're the same, right? Like they're the same time. Yes. Yeah. It's our own binary format. So when you build your custom model, you'll persist that representation at whatever that framework is. So if you, for example, train it in MXNet, it would be JSON. You train it in TensorFlow, it would be a protocol. And then Cafe I know the least about, but I think they have their format too. But when you bring it into H2O, we have our own format that we use for scoring and I don't know, deep water team in the office is a Java API for that. Yes. Yes. Yes, sir. Today, no, but we are continually integrating all our products, right? Or all our solutions, I should say. So the first release, no.
The problem is that you save the format and then again put it back into the. So I'm trying to see if I can combine all the shares in the back. Like now you need data that again put it back.
Well,
I would say pipeline.
yeah. So we already need data, right? Yeah. But the Mojo or what we have is a network, not data. Good. So I mean, that'd be great to have everything work in one unified way. Good. We're working towards that.
So I think it's more unified that in a very nice way.
Yes, exactly. That's our big value prop. It's continually integrated. Yeah. Oh, it's not supported in terms of officially. We're working on it. We're still working on it.
So where do I get it?
Yeah, we don't have it in that version. Okay. Yeah, we're still we again you have to do a lot of testing, things like that. Yes. Any other questions? Well, feel free to stay, hang out, come up and ask me something. Hi,
Brooke.
Hey, Brooke. Nice to meet you.
Well, a question about it's kind of incomplete knowledge, but in the context of the fraud example of Wells Fargo, when
I didn't say Wells Fargo. Yes.
Banks have standardized data.
Yeah.
You finish your training model, you now have the ability to do the protection
Yes. Yes.
What part of that is transferable from the H2O point? Is there a
Transferable as in like.
okay, now we're done. Can you do it for everything? What element of the experience belongs to H2O and belongs to the bank? And where's the sort of boundaries for reusability?
Well, so technically, that there's no technical limitation. Like technically, if I train the model on like Wells Fargo data,
It's only good for that data. Yeah.
well, no, I could take that. If Wells Fargo didn't care, they could say, here, you need to like, pick your other favorite, Chase Bank, JP Morgan, whatever. Use this model and you train one. Like technically, that's no barrier. We don't hold any of that, right? We have NDAs. We just support them with their platform. They own the models, they own the data, right? And it's just regulated. So the only thing that we carry as a company is just me having knowledge, kind of working on that problem, and being more efficient the next time another customer has a similar problem. That's really all it is. But I'm tied to NDA, like I can't share any specifics. That's about it.
Is there an emergence of a horizontal layer sometimes where you can
We're trying to do that. You should watch our CEO speak. He's saying that horizontal is the new vertical. That's exactly what he's talking about. Is that why are people solving the same problem over and over? And we should come up with, but it's the classical standard. Like everyone kind of wants to protect themselves. And like, yeah, it's my goal. Exactly. They want to influence kind of what's important to them.
They want to be fun.
Yeah. So yeah, sure. Hi. Hey. Yeah, you did that. Yeah, I was there. Yes, great job there. Yes.
So yeah, we have meetup, but if you are
Okay.
so if you're
Outcast. Vivian.
I'm Stella.
Stella,
You know
that's right.
training, right?
Yeah.
I'm the co-chair of it.
Yeah.
So I think sometimes,
Okay. You find it good? Good talk?
I'm not quite understand, but I bring a bunch of my friends.
Sure.
They are working on GPU.
Sure.
So, and
Yeah.
I'm computer science, but I'm doing business.
Sure.
So I think I contact one of you guys, but I'm not sure. I'm not sure.
Yeah.
Okay.
We can get hold of you.
Yeah, I'll just connect with them.
Okay. Sounds good. Hi. Okay, great. Yes. Okay. Yeah. Okay. Okay. Thanks for joining. Hopefully you enjoyed the session. When is that? Yeah. Yes. Sure. Yeah, absolutely. I'll follow. Thanks for coming. I don't. I actually do in the office. I have to go in the office, but just do. This is my first name. It's my first name, Wen. Yeah, and it's at H2O. Cool. Thanks for coming. Great. Thanks for coming. Yeah, we were doing that a lot before, and we just. But yeah, we'd like to. Thanks for coming. Thank you. Hey, Chris. Okay. Yeah. Ah. Yes. Yeah. GPUs are fully custom. They're optimally designed for deep learning and specific use. GPUs don't have to be used just for